Hi everyone. In this video, we will see about bioelectric signals and electrodes. To start with, what are bioelectric signals? Bioelectric signals are the signals that are present in the human body, and when we measure these bioelectric signals, we will get to know a lot of information about the human body and the organs associated with it. For example, if you take ECG, ECG is electrocardiogram, which is actually a measurement of the bioelectric signals that are concentrated on the heart muscles. So when we acquire this ECG, we will get to know how the heart is functioning. Likewise, we can analyze different organs like the brain. We can understand how the muscle fibers work. There are also bioelectric signal acquisition in near the stomach region, which is EGG, and then we have EOG for eye, and there are so many such things. Right? So here in this video, we will see about how to acquire the bioelectric signals without um, having any noise inside it, so that we will get to analyze the pure biosignals, the pure bioelectric signals from the body without any noise for uh, manipulating or for analyzing and for predicting different things. To start with, we should know about electrodes. Electrodes, we all know that we have already heard about this word, we would have already used this word, but now let me give you uh, another definition to help you understand what electrode is. So to me, electrode facilitate the transfer of ionic conduction in the tissue to electronic conduction, which is necessary for making measurements. So that is what an electrode is. In our case, we will be using this electrode to transfer ionic conduction in the tissue, whether it is under the skin or most 90% of these cases it is under the skin. So from that place, from the tissue and ionic conduction, from the ionic conduction, there's a transfer of ions to the electronic conduction through the electrode to the measuring device. So we will have this ions transfer. This transfer of ions, when we learn, when we manipulate, we can understand a lot of things, right? So doing this is actually the electrode, which is a pure conductor. Now, if we take this recording electrodes, there are two types actually. One is surface type, the other one is deep seated electrode. So if you say about surface electrode, they are on the surface of the skin and they will not damage the live tissue, right? So when we go to hospital, if doctor wants to take ECG, if they want to measure ECG or EEG, in most of the cases they use this kind of electrodes, which is surface electrode. And there are also cases where they may have to know much more information. In those cases, they will pierce through the skin and take signals from from the depth of the tissues. So in those cases, they use this deep seated electrodes. So they actually, this deep in the seated electrodes, they indicate the electric potential difference arising inside the live tissue or cell. So these are the two important types of recording electrodes. Moving forward, we will learn about the electrode tissue interface. We have we have just seen that electrodes acquire biosignals. Very true. But now we should know whether the electrodes pick up only the biosignals, or will there be any other extra information that will be picked up by the electrode. So to know that, we have to understand the interfacing points, the electrode tissue interfacing points. So how many, if you look this properly, we'll get to see, know that there are two interfacing points. So actually, we typically utilize a surface electrode to capture biosignals. During this process, we apply an electrolyte gel. So this is a gel which we apply on the electrode or on the skin, or you can say gel layer is put in between the electrode and the skin, right? This method generates electrical disturbances, which are um, unwanted noises, motion artifacts, contact impedance, and all those things, right? So those will create electrical disturbances, or it will create unwanted potentials, unwanted small values uh, embedded into the original biosignal. So we have to work, or we have to create a setup in such a way that this electrical disturbances are removed. So how to find out the electrical disturbances? To start with, we will see that one by one. First, we are going to, this is the entire thing, the electrode tissue interface. In that, we are going to see the interfaces. So there will be an interface between the electrode and electrolyte. We are going to call it as electrode electrolyte interface. Similarly, there will be another interface, electrolyte and skin interface. So that will be the layer or the interfacing area between the electrolyte and the skin. Now let's start with electrode electrolyte interface. So this is our electrode. This is going to be the electrolyte, or you can also call it as gel, electrode gel, or paste, jelly. People use different names, but technically we consider it as electrolyte. So if we consider this as the skin, above the skin we apply gel, and above that we have the electrode. Now our focus is on this region. What is happening between this electrode and the electrode gel? So if you see, when I place this electrode on the gel, this electrode has some kind of ions. They have loosely packed ions. Yes. Similarly, the gel will also have loosely packed ions. When they are put together, the ions will diffuse, or they will move, and they will reach a saturation point where outside the electrode will be a layer of positive, and then a layer of negative, a layer of positive, negative. Similarly, inside it will be layer of negative, then positive. It goes on, right? So now if you look at this, you can see that this setup, the uh, positive here and then negative here, it will be like two parallel plates separated by a dielectric medium, right? So we can consider this setup as a capacitor, right? So this was actually learned by Helmholtz, and he named it as Helmholtz double layer. So there's a tendency for each electrode to discharge ions into solution, and for ions in electrolyte to combine with each electrode. The net result is the creation of charge gradient. Charge gradient is the capacitor, right? So I can represent this thing as a capacitor. So what I'm going to do, or what I have done here, is I have converted this into a equivalent circuit. It's not a circuit, or you can consider this as an equivalent electrical component. Now we will understand it better. I have to read on the diagram. The electrode, this is the charge layer. Now imagine there is a signal coming from here or from the other side, all from either side. Let's consider it's coming from here. When the signal come here, there will be small resistance at this point. So I have added a resistor, and then we just saw that electrical equivalent is a capacitor, and then there will be some potential here, there will be another potential, so a potential difference is created. So we have added another voltage source, right? So we have the electrical equivalent as a voltage source, a capacitor, and a resistor. So I can represent this thing, or this electrode electrolyte interface, as a combination of a voltage source, a capacitor, and a resistor, right? So how to connect that, we will see that. But before connecting into that, this depends on the type of electrode we use. So we have to choose the electrode. The electrode that we choose actually plays a very important role. If you see any measurement with electrode, there will be two types of electrode. One is the testing electrode, the other one is a standard electrode. Okay, so you would have seen, or you would have heard something called reference electrode, the standard hydrogen electrode. So this is one of the most commonly used electrode, because the potential of standard hydrogen electrode is zero. That way we can easily calculate the difference. We usually find the difference, right? So the difference can be easily calculated if we consider a standard hydrogen electrode. So this table shows the electrode potential of different electrodes. So if you see, hydrogen has zero. So this is the reason why most of the cases they prefer hydrogen electrode. But based on multiple research, they found that the difference in the half potential that exists between two electrodes. I'm talking about two electrodes, not just one electrode. As I said earlier, there will be two electrodes. One is testing electrode, and the other one is a reference electrode. So the difference between these two electrodes should be zero actually, right? But in most of the cases it will not be zero, and that value we call it as offset potential. Without even measuring the data, it shows some value, so we call it as a offset potential. And this scientist, they worked a lot, and they came on they found out that this particular electrode in the solution is found to be the most effective one. This is silver in silver chloride is found to be most effective, which you can see from this table. If I use stainless steel in a saline solution, the potential difference between the two electrodes is 10 millivolt, which is I mean the offset potential is 10 millivolt, which is very high. Similarly, if I use silver, just silver in saline solution, it is 94. If I use silver chloride in saline, 2.5. But see here, the silver chloride in ECG paste is only 0.45 millivolt, which is very low. Whereas if I use the same in a sponge setup, then along with ECG paste, the value will be much smaller, right? So we have to choose the appropriate electrode, right? So now consider we have chosen appropriate electrode. Now we are going to see the electrical equivalent, which we just discussed above. This scientist Warburg designed this electrical equivalent. He actually initially designed as a resistor and a capacitor. Later he understood there was a small leakage, so he used Faraday leakage resistance, and then he realized it's not just him. A few other scientists, they understood and they modified Warburg's equivalent circuit, and this final, the C, is considered to be the electrical equivalent of the electrode electrolyte interface. And this is also not the entire thing, is just a half cell potential, which means for one electrode this will be there, and for another electrode you have to draw another similar setup. You'll understand when we move to the next slides. Now that we have seen the electrolyte interface, we will see the electrode tissue interface. So we saw electrode and electrolyte, how this electrode and gel reacted. Now we have to see how this gel and skin are going to relate, or how they are going to react. Right? So to know that, we can see that we can understand that when skin and electrode are separated by a small thin barrier, in our case it is the skin. So there will be electrode, which is a gel, and there's a skin. Beneath the skin there will be some kind of a liquid medium, right? So this liquid medium will have loosely packed ions, gel has loosely packed ions, so this ions will try to jump from this layer to this layer, and that jumping is supported by the skin, right? So now when it jumps, it produces small voltages, a tiny voltage, and it is not from the body but because of the interface of this tooth layer. So those potential we called as contact potential. So in the electrode electrolyte interface we saw offset potential. Here we see contact potential. So this should be electrode skin interface. Ignore this, it's actually electrode skin interface. And again electrode skin interface. Now this can be seen as two conductive medium on either side of the skin, giving two opportunity, which means the entry of the uh, ions can be two-way. One is it can be like through a capacitive action, since we have two mediums separated by a dielectric kind of thing, where skin is the dielectric. That is one option, and another is through resistive action. Directly it can pierce through the skin, right? So there are two options, so both are available simultaneously. So they have drawn a equivalent circuit like this as capacitor and resistor, and these are because of the body tissue and the fluid, right? And then comes our signal, which is our interest, signal of our interest. If it is ECG, if it is from heart, ECG, if it is from brain, EEG. So those signals we call it as EB. So this EB is the actual biosignal, but we also get some interference or disturbance from this CT and RT. So this will create unwanted noise, right? So this I have put everything together. Now the entire electrode tissue interface, if you see, this is at the electrode skin interface, and this both are the electrode electrolyte interface, right? So if we put together, we will get an electrical equivalent like this. Now here we can put different values based on different skin types, based on the type of electrodes used. We can have different values, and we can simulate and understand what will be the effect of the impedance provided by the electrode, right? So based on these values, we have to choose the most appropriate, right? Moving on, uh, we saw these two important terminologies, contact potential and offset potential. So we should not get confused about it. So to understand better, I have added another slide which is contact potential, which says that the voltage created at each single electrode skin interface at this point. And offset potential is the difference between two electrode contact potentials when used together, right? So both are not favorable. We have to devise a system to nullify both the contact potential and the offset potential, right? So how to know little more, to have more technical discussion on this, we can say the electrodes are polarized. What is polarization? Sometimes charges build up at the boundary, and this charges will move, and it will create a battery kind of a setup. So if it forms a battery kind of a setup, we can say that as a polarized electrode. The effect is called as polarization, right? And based on that, we have two types of electrode. One is polarized electrode, the other one is non-polarized electrode. If the charges are stuck, the electrode acts like a capacitor, and it's bad because if there are any DC component, capacitor will not allow DC to pass through, right? So this is bad. So polarized electrodes are not usually preferred. Whereas if you take the other one, the non-polarized electrodes, they actually let the ions to freely move in and out, so that biosignals can freely go out and come again, right? So those are non-polarized electrodes. So again, earlier we saw recording electrodes types, surface and depth. Now we have another classification, polarized and non-polarized. So understand, polarization is when the charges build up at the boundary of the electrode, right? So with this, I'm stopping this presentation. We'll learn much more about the electrodes and its type in the next video.